Hi guys, today I'm going to talk about using the Link Laser Link system to talk to PLCs and other automation devices using Modbus RTU. The presentation will take the form of three main components. The first is a recap of a previous video I did, and that was showing the Links system running on a Raspberry Pi. You can actually go back to that video if you Google YouTube real-time control Raspberry Pi and do a search on that. We should come out top of the list, or you should go to the URL indicated there, and I'll put that in the actual comments below. Then I'm going to do a demonstration of how to set up Modbus RTU within the Link system, and finally I'll do some conclusions. But just to recap, Link Laser owns the IPR for an enterprise SCADA system. We developed it a long time ago, and we have something like 40 man-years of software development effort put into that product. It was written to be fully POSIX compliant, and therefore it's easily ported to POSIX compliant OSs, and we've already got it running on various OSs such as Linux. The system basically could handle up to 65,000 data points. It could acquire data on 25 data acquisition links, each with different protocols if you desired. It can handle 0 or 1 screens. In a 0 screen configuration, it's a black box acting as a data concentrator. It can do unlimited calculations. It can do alarmed event handling, and we have the ability to write customer applications going through an API that we provide so that you can customize the product. All of that is expected to be updated within 1 second, and if you go back to the original video, you'll see far more details on that. So I've already done it once, I won't elaborate on that anymore. But just basically, if we're looking at the overview of the software, everything centers around a real-time database, and this is the database that holds 65,000 objects. Data is actually pulled in from various sources, the primary source being the data acquisition subsystem. And here we have a standardized interface, and we can write different drivers to different devices. The one I'm going to show you today and what I'm going to concentrate on is Modbus. So we're concentrating on the Modbus, data acquisition and database. Although I will touch on a couple of the other applications just to give you a better feel of how things can be used once they're being acquired. But I'm going to run on a Raspberry Pi 3, and Links will be running on this product. I'm going to use a Cubloc PLC. This is a product from a company called Comfile, and the one I'm going to use is a CB405RT, which is a PLC that can handle around about 60 I/O. So I'm going to plug that into a study board that's also provided by Comfile, and the study board will bring out a few of those I/O in the form of push buttons, LEDs, etc. So on the Comfile board, I'm going to use 4 push buttons for digital inputs, another 4 slider switches for more digital inputs. I'm going to use LEDs for digital outputs, and I've got 2 one-turn pots that are going to be my analog inputs. Modbus is the connection between the Raspberry Pi 3 and the Cubloc study board, and we'll be able to control these devices based on a program that I've actually written within the 405RT. Firstly, we need to know a few fundamentals about Modbus. Basically, there are 3 types. Modbus ASCII, not used very much anymore. It was the forerunner of the Modbus series of protocols, and it's been superseded by a large degree by Modbus RTU, which is basically a binary protocol, does effectively the same as ASCII but is far more efficient. So ASCII sort of dropped out of favor a little bit, and the RTU, the binary protocol, is the one that dominates the industry at the moment. There's also Modbus TCP, which is basically the binary protocol running over Ethernet. The commands are similar, it's just a setup of the hardware that's slightly different. Modbus TCP is a little bit more expensive to implement because the nodes are not as cheap as they are in general on the RTU front. So I'm going to concentrate on Modbus RTU. But irrespective of which protocol you're using, basically there's two things you need to know. Data is effectively stored in memory area, and the memory areas are broken into 4 blocks. So for example, the first block with a memory range between 1 and nearly 10,000 is actually allocated for what they call coils, or discrete outputs. The next block, 10,000 to nearly 20,000, is dedicated to discrete inputs. So this is where we have the inputs from the process stored. Block 30,000 to nearly 40,000 is dedicated to analog inputs. They're in registers. And block 40,000 to nearly 50,000 is dedicated to analog outputs. So basically, analog inputs, outputs, digital inputs, outputs are stored in these regions, and these are the regions that we read when we want to read data from the node. You can see that for some, for example, data for outputs, we can do read and write to the actual register. For inputs, it doesn't make any sense to write to an input, so we can only read. And the same with analog inputs and analog outputs. The other thing you need to know is that when you're talking to the actual node, you need to tell it what you want to do. So for example, there are a number of function codes. I've not listed them all here. These are the most common ones. So for example, function code 05 will read a single output coil, or a single output, from the 1 to 10,000 register range, and that will then be passed back to the Modbus master. You can do multiple reads, you can do multiple writes, etc. But the basic format of the message is you tell it what node you want to talk to, you tell it what function you want to perform, you tell it the memory address, and then you send a CRC to check the message. The affected node reads that and then sends the required response. So now I'm going to talk about the Modbus setup, and I'm going to use the actual hardware to do this. The first thing I need to do actually is on the Cubloc, and I need to set up the actual information within the PLC. So Cubloc is a device that is able to be programmed either with ladder logic or with BASIC. If I go to the ladder side, you can see I'm not using any of that. I'm just using the BASIC to do some really fundamental operations. And the first thing I want to do is I want to specify which COM port I'm actually going to use. Here I'm going to use COM1. There are 3 channels on the 405. I'm going to run it at 115,200 bits per second. The 3 indicates it's 8-bit, no parity 1 stop bit, and the others are buffer addresses. And then we got the set Modbus command. The 1 indicates I want to use Modbus RTU, and then what node and what link. I won't go through the program in detail, but basically then the rest of it is I want to actually read the actual input from the A to D converter, and then I want to store that in a certain register, in this case register 10. And then I want to go through a loop and keep reading it every I think it's 2 seconds here. I should really decrease that to less than a second. Get far more response. And I'm doing that for the 2 analog inputs, but I'm also doing it for the digital input outputs. And here what I'm saying is A is going to be input 0. If A is 0, then we're going to set the register 8 low. Otherwise, we're going to set it high. So in other words, what I'm going to do is I'm going to look at the status of the push button or slider switch, and if it's in the off position, I don't do anything. If it's in the on position, I light one of the corresponding LEDs. So that's basically all I need to do to set up the Cubloc. And we can move that out of the way now. Then what I've got to do is set up the links, the process control system. And to do that, what I'm going to do, I'm actually running VNC here on a PC, and the only reason I'm doing that is so that I can do screen capture. I'm actually running under Windows, and I don't have a very good screen capture on Linux. So I'm running the PC basically just to do the screen capture, and to be able to capture the screen, I'm using VNC to mirror the Raspberry Pi 3. Before I go ahead, let's just have a look at the hardware. and here I'll just put a window in the bottom corner that shows the actual system I'm running on. Over here I've got the headless Raspberry Pi, and that's connected via a serial cable to USB, actually to the Cubloc, which is supporting the 405RT. That's basically all I've got. At the bottom you can see the push buttons, and the program will run so that if I press push button 1, the first LED lights, push button 2, etc. If I move slider switch 1, the 5th light works, etc. So basically that's the input-output subsystem working, and we'll come back to that in a little bit. So now going back over to the Raspberry Pi, the first thing I need to do is I need to start links. The screen's a bit jerky, and that's because I'm using low frame rate and I'm using VNC. It's actually far faster on the Pi, but never mind. So the first thing I want to do is start links, and I use the console to do that, and the command is simply slinks, and I'll run that in the background. If I look at the log, and you can see that the link system starts a number of background processes, including loading the database, starting the alarm event handler, setting DB outputs, database outputs, setting a scheduler, running the alarm events, starting calculation lists, etc. So links is actually running, and if I now go to the maintenance side, this allows me to actually configure the system to talk to Modbus. So the first thing I need to do is specify which port I want to run on. So I go to the Tools menu, I go to Serial Ports, and I've already set up the port I want to run on. I've done all this in advance because I'm a pretty lousy typist and I don't want to bore people while you watch my mistakes being corrected. But if I go to the link and edit it, you can see how it's been set up. The Linux system uses devices to use for comms ports, and typically it's a TTY, usually S0 or something. In my case it's TTY USB 0 because I'm using a USB to serial converter. I set my baud rate at 115,200. I can set it to any other parameter I want. No parity, 8 bits, 1 stop bit, and I tell it it's a data acquisition link. And the reason to do this is we can have all kinds of different links in the system depending on what the port's supposed to be doing. So it can be a terminal, a printer, it could be links data acquisition, etc. Okay, so I'm not going to change any of those parameters, but what I can show you is that we have the ability to define up to 128 different comms channels on the links system. Okay, so that's all I need to do now to set up the actual physical port. And now what I need to do is I need to set up the actual objects that I want to be acquired. Again, I've done this in the background before, but the first thing we need to do is go to the database and create the objects that are going to be stored in the link system that we're going to acquire from the external source. If I go to database list, the objects I've set up all begin with ST. ST is short form for stealth. It's a new piece of hardware we're working on, and that'll be coming to the market fairly soon, and it'll give the people the ability to have all this thing largely set up without doing anything. So on the Cubloc, what I've said is that we're going to use 8 analog inputs, 0 to 7, 8 analog inputs of low resolution. These are 10-bit A to Ds. And the first 2 are the actual pots that you remember on that board. Next, we're going to actually set up digital inputs, and I've actually specified 16 of those, 0 to 15, and I'm only going to be using 8 of those also. We also set up digital outputs. Again, I've set up 16 of those. For short measure, I've set up some high resolution analog inputs. The Cubloc 405RT has a high resolution A to D, so we can bring in values at 16-bit resolution. I'm not actually going to use those today. but nevertheless those are available in the future. And I started doing pulse width modulated outputs for analog, and then I realized that the study board doesn't support any, so I gave up and basically I abandoned that process. So if you remember, the first thing we want to do is we want to set up the analog inputs. These are the two primary things that are going to give me data from the board. And if I go to the analog object definition part and I type in the name of the ones that I've already done, it retrieves that information, and you see that some information is grayed out. For example, I can't change the object type and I can't change some other parameters because primarily this has already been put onto a data acquisition link. The use count is already 2 within the system. It's already on a link and it's already in a calculation list. And if I just go changing things willy-nilly, I'll leave abandoned references or orphaned references all over the place. So it checks what the object count is, and if it's 0, then I can modify anything. If it's got a use count already, then I can only change certain things. So this is my main name. This is an extended text to give me more information. I already specified in the past it was an analog input, and I've not put it into any particular process group, so it's going to default to all groups. My data shape is going to be 3-2 because what I'm going to do is give it an engineering range of 0 to 100, and the units are going to be percent. So I can show up to 100.00%. And down to 0, of course. But if you remember, we're talking about a 10-bit A to D coming off the Cubloc, and a 10-bit A to D will give me that particular range split into 1024 increments. So I'm going to receive an integer from the Cubloc with a range of 0 to 1023. So what I'm going to do is use that to specify the integer value coming from the Cubloc. That's going to be my total range, and then I'm going to map that to the engineering range. So for example, 0 coming from the Cubloc will be 0%, 1023 coming from the Cubloc will be 100%. The only other thing I've done on this object, I've given it some alarm limits. I can have up to 7 limits, and I've specified 6 of those. And the point is that I can show it's fairly easy to take a value and I can put an alarm limit on it, and then we can pass that to the alarm event handling module without writing any code. So that's the definition of the analogs. The digitals, are far simpler. So if we go to, this is stealth digital input 0. It's digital input in the default process group. I've given it the text of off in the opposition on in the on position. It's got a use count of 1. I'm using it on a data acquisition link, and you can see it's coming in on the link I've nominated as stealth, and it's coming in on the node that I said is main control. So we've got some database objects set up. We've got our physical link identified. Now the next thing we need to do is actually tell the actual node what objects I want to acquire and in what order. So we go to the data acquisition module, and you can see I've got 2 set up. The first one is the stealth link we've been talking about. It's inactive at the moment. It's inactive because I want to show you how to set it up. I've also got another link, which is another Modbus link, but this is a USB to 485 converter, and that has got 2 nodes on it, and I'll show you that in another video because I want to keep this video as short as possible. So if we go to the first link and we say show nodes, I've only got 1 node actually defined. I've called it main control, and if I want to edit it, I simply go over that. I tell it it's a PLC. I tell it what the cycle time is, how many retries in case of a line failure, what the timeout period is, etc. So this is for the actual node. If I want, I can do an auto start. I'm not going to do that. I want to show you how to start the thing up. By the same token, before I go there, if I go to the edit link for the whole link, you can see that the protocol is defined here, and we have a drop-down list of different protocols we could set up. So, for example, I could put in Modbus TCP. I'm not going to do that, but we can have different protocols for different links. So the link defines the protocol, the node defines things like retries and that kind of stuff. Do a cancel there. Okay, so we've got the actual link defined, we've got a node defined, and now what we want to do is put objects on that node link. So we go into the edit objects, and you can see I've already set up some of the objects for this link. If you remember, we had in the database we had stdi 0 to 15 for digital inputs, and I'm using 8 of those. And again, if you remember the Modbus registries, they're coming in at 10,001 roughly up to 20,000. So my first digital input comes in at 10,001. Now, here's an interesting thing that I'm not quite sure about on the Cubloc. Normally what happens is this input reference 10,001 is a word, and you can specify which bit in the word represents this input. By that token you can say I want to read one word and I can get 8 inputs at the same time. But the Cubloc doesn't seem to do that. It seems to want a digital input or an output for each word, and that's the way I've set it up. Now it's very inefficient, but we don't have very many I/O on the Cubloc, so it's not going to be a killer for me. So I've set up 8 digital inputs with values 10,001 to 10,008. I've also set up digital outputs. Again, if you remember from the Cubloc side of things, we basically can only read from a digital input, so we can't set an output reference. But on a digital output, we can read and write. So I can tell it where it's getting the value and what value I'm going to write to if I want to write. And if you remember, outputs were from 1 actually to 9,999. So here I've identified 8 outputs, and they're coming in the same token as the inputs, but I can now write to them as well. And then I've just identified the 2 analog inputs, so they're coming in at 40,000. But again, because the Cubloc uses some registers for the first 10 registers for other things, it's actually coming in the 10th register, and because I have to have a 1 offset, for me it's coming in at memory address 40,011, and then the second one comes in at 40,012. If I go to this one and edit the object, you can see how this is all set up. You tell it the object name, you tell it what the reference is. If it's an output reference, you can do that. I can't do that on an input. You tell it how big it is, whether it's 2 bytes, 4 bytes, whether it's a float. In general, we don't get floats from Modbus, but remember this is set up for other protocols. I can also bring in a bit group, which is another type of signal that other PLCs can give us. So we set all that up. We tell it what the pole frequency is for this particular signal, and when we say OK, that's all set up. Okay. Now I say we can set up the pole frequency for the signal. We might not want to acquire analogs every second. We might want to acquire them every 5 seconds or 10 seconds. So the actual link frequency is 1 second, and if I say that the pole frequency for the signal is 1, it's going to get the data every second. But if I say the pole frequency for this particular analog is 5, it's going to go for 5 cycles of the link before it actually then picks up the analog, and the same with the next if I want to do that. So I can actually reduce the load on my link if I want by only acquiring signals at a frequency that's useful to me. Okay. Okay, what I want to do now is simply start the link. So I go over the particular link. For good measure, I'll restart the Modbus server, and then if I go to start link, you can see the link becomes active, and if I show nodes, the node itself is active. In other words, I can actually start a link and start individual nodes, but In this case there's only one node, so I start them both at the same time. So if I go to statistics, you can see that I've already written 115 blocks, read 125 blocks, etc. Positive acknowledgements, no errors, no timeouts, and we're acquiring those signals. And you can also see the percent load on the link, and taking about 3% load to acquire 16 signals. If the Cubloc worked in the correct way and we could stuff the bits into 1 byte, it would be a lot better, but I'll work out how to do that later. Might have to talk to Cubloc. If we go to the vlog again to have a look at the information, you can see what's been sent by the Modbus RTU server. So we get node link, node 0 for example, function code 2, address blah blah blah, and then the CRC, and then you can see the response coming in. So everything's working fine, and now what I want to do is just show you how we can make use of that data as we come into the system. So let me minimize the terminal, and if I can also get rid of some of these windows, what I want to do now is go to database, and I have a function I touched on before called database view. Within links I have a program called database view, and I've input the relevant signals into that particular application, and database view allows me to see the actual values in real time coming through the database. So set up the 2 analog inputs, a digital input and a digital output. And if I go to my iPhone, my little window in the bottom again, and I look at the Cubloc study board, you can see if I press the first button, the first light indicates, and also if you look on the database view, you can see the status change there. By the same token, if I move the first pot, you can see the value in database view will change. And also if I change the second pot, database view changes on there as well. So everything's working as it should, and I'm getting values coming through the database, and you can see I can affect them directly from the Cubloc. We've got the values defined in the database, and we've actually got them being acquired from the Cubloc on a Modbus link. Let's do something a little bit more interesting and show how other applications within the system can actually make use of that real-time data. So if I go to my Mimic editor, for example, basically what we need to do is tell it what kind of field we want and where we want it positioned, and then we'll specify where the value is coming from. So we'll have a dynamic field, we'll position it on the screen here. Comes up as undefined because it doesn't know what data to link to yet. If we then modify the properties of that field, we can then put in the value that will update it. Apply that, and you can see that we're now getting the value coming in from the pot. I can modify the field properties, for example change its font to Robo, we can make it bold, we can change its color, let's make it blue, and change the size, and apply, and you can see the field will go to the attributes that we define. Okay, if I want to pull in the other value that I was defined in the database, again I go to define where I want the field to be, and I then say properties, and we want to make this one, let's say AI1. And we're going to make this one green, and we'll make this one big as well, so we'll make this one, I don't know, 60 point, make it bigger, and apply. So you can see we just put the values on the screen where we want them, and if I turn the pots, you can see those values are going to change in line with the value coming from the pot. So it's as simple as that to actually put values on the screen. Of course, if we want to move them, we simply put them somewhere else. It's no programming to do, basically, just fill in the blanks. So let's come out of that now. I won't save it. But what I do want to do very quickly is just go to the final thing I want to show you, which is go back into Maint. And we can, for example, show those values coming in and being processed for alarms. So if I go to the alarm list, you can see the format of the list. The blue indicates that we've got a whole series of alarms that are linked together. But let me increase pot 1, which is AI1. And if we go up, we can see we've transgressed a couple of limits. And what this shows is the date and time of the occurrence, the value that made it go above the limit, the value, which way it was going. It was still going positive. It's crossed the high and the high limit and the high limit. It's a repeat alarm. It's got percentage units, no process group and priority, and then the extended name. If I come back down, bring it back into a normal state, you can see it puts the thing in blue. Basically, all we're saying is we've got a number of repeat alarms, and if we want to acknowledge all of the alarms in the list, we can simply do that, and the list goes green, saying that we've actually recognized all of those. By the same token, if I turn pot 0, we get a new alarm, and this time I've passed the low limit. So it's fairly simple to actually specify what data you want from a PLC, and then link it to the other applications within links to actually build up your man-machine interface. Okay, so let me wind up this now and get rid of my VNC and simply say, as a conclusion, okay, we can use Modbus, we can use other protocols. Modbus itself is a very simple protocol. It's used in millions of nodes worldwide. It can be used over serial, Ethernet, wireless, etc. So it's got a broad popularity in a number of different types of industries. But like all protocols, like all communications, you've got to get everything right for things to work. So whether the wires are crossed, what the baud rate is, which port you're coming in on, how the signals are defined in the database, how the signals are defined for the link, etc. It's no different from any other protocol. But the tools that we provide make that as easy as possible. As far as the Raspberry Pi is concerned, what we're trying to illustrate here is that we can use these maker boards for serious process control applications, providing we use industrial grade software. So that's the whole point of the video. I hope you enjoyed it. I hope you got some information from it. And if you've got any questions, you can actually address those to sega.com.my. If you go to the contact page and fill out the form, we'll do our best to get back to you as soon as we can. Thank you very much for watching. Hope you enjoyed it. See you soon.